Hello, we are back to. I believe that this will be the last clip for our lecture one, okay? Since we cover most of the file or document attached here, okay? So our last topic that we're gonna end for our first lecture here, the group of lecture one here is dealing with finding the dual variable when you solve this type of two-stage linear programming model. Okay. Uh, Again, we go back to the classic model here. Okay, and as you know that when you have a combinatorial nature of the total number of uncertain situation, okay, scenario, the number of scenario, okay, and you end up, the A metric end up getting to be contained with a large amount of row, the constraint, okay, but the decision variable might not be that much in terms of column, but the additional variable of u and v, as grow, keep growing as the number of constraints grows. So that leads this to a very special case of a large scale linear programming problem. And so far, we already showed that it will be much more efficient to solve this type of problem if you apply the Bender decomposition. Okay, and we show you the experimental problem on, the randomly generated problem and classical diet problem, and also an example from the original Danzig's paper. And you know that Bender result can be very efficient. Okay, but as you might study the linear programming before, that we for the regular simplex algorithm, once you solve the original LP model here, you will get both the optimum solution and the optimum dual solution of problem at the same time. Okay, so our question is that when you apply the Bender decomposition here, okay, as an iterative process, certainly for each iteration you get the new y star, which is the dual variable for the decomposed problem here. Okay, I mean, you already identify x star, so therefore you get a new y star by solving the decomposed problem once you cut partition x star x variable out and solve the remaining u and v. Okay, and it's not the y star is not the optimum dual variable for this one. Okay, so but it's related a little bit if you go back and listen, and then rethinking about the theoretical behind the linear programming. So I did a summarization for when you want to find a dual variable when you solve the LP problem from Bender decomposition. We're gonna go back, okay, in this one we and look back at the iterative process, and when you keep solving the adding this Bender cut, okay, and certainly if you have an additional deterministic constraint that not related to any uncertain situation, you can add it up here. Okay, just like what we did in stochastic diet problem, when you have summation of x is equal to 1 and x have a lower limit and upper limit, okay, control. Okay, so but in each iteration, this optimality cut constraint keep increasing. Okay, from I equal 1 to I suppose that the m star is the number of iteration. Okay, for the Bender decomposition process, and you end up after m star, you have the m star number of constraint for the Bender cut. Okay, and with the requirement of t, okay, the additional variable of t, and t can be unrestricted. Don't misunderstand that t have to be greater than or equal to 0. You never know, because t is according to the objective function. It can be negative, can be positive, whatever. okay, but x is certainly by default is greater than or equal to 0, okay. I'm going to look back and assume that for each iteration here, okay, even though the number of bended cut keep increasing, okay, and suppose that when you solve this problem as a regular LP, okay, with any application of the available software to solve the LP, you get both the optimum solution for the primal model and the dual model at the same time. Okay, so I would assume that lambda sub I be the dual variable of this model. Okay, and I didn't consider any additional constraint down here, so lambda I be the dual variable, okay, as the number I equal 1 to m star also, okay, according to the number of constraint here. Therefore, the dual problem of the above model, okay, so I just write the dual problem for this model, okay, this bended cut model for optimality cut here, okay. So the right hand side, okay, become the objective function here for each b transpose times yi transpose, okay. This should not be yi transpose, should be yi, okay. I forgot to erase this should be b transpose yi, okay, not yi transpose, okay, so mistake, okay. B transpose yi, okay, should be yi star, okay, even, okay, yi star I, okay, not transpose here, okay, just make it as a star, okay. For each right hand side I, okay, you time lambda sub I here, okay, and you get with the coefficient of each constraint you contain the variable t, okay, all constraint, and the coefficient that multiply t from the left hand side is 1, therefore you get this one, lambda sub I is equal to 1, summation lambda sub I equal to 1, okay. Make sure that this is, you understand it, this is not yi transpose, it's yi star, and this is what should be yi star, okay. It's a mistake from my typing, okay. Because in each iteration you get the new yi star, okay. When yi star is you might recall is a vector of the dual here, okay, this one. When you're solving this, you get the new y star, and for each iteration I, okay, we call yi star. So this is not transpose, is a yi and superscript of star, okay. And summation lambda I equal to 1 is because of this, in each row, the coefficient and multiply t is 1. So you get lambda sub I equal to 1. That's actually it's a transpose, it's a column vector, so you transpose it to become the row vector here. Okay, and also for each coefficient that multiply to x here, okay, you end up summation I equal 1 to m star of yi transpose a minus c transpose times lambda sub I have should be less than or equal to 0, because the reason is 0 is that because we don't have any coefficient of x in the objective function, okay. With this consideration of the and certainly an additional constraint of lambda I is lambda I have to be greater than or 0 for all I, okay, because all the constraints are all related greater than or equal for minimization. So when you transform in the dual form, become the objective become maximized, and the inequality side can be reversed, like lambda greater than or equal become less than or equal here. Okay, if you really look at the formula of the dual here, okay, I can just combine lambda I and yit here. Since b transpose is a constant value, not relying on the index side. So the objective function will become b, I put the b transpose outside, w equal to b transpose summation I equal 1 to m star of lambda I yi transpose, okay. And lambda I can be either on the front or on the back of multiplication, because it's a single scalar value, okay. And also lambda sub I equal to 1, and I can do it again here, okay, here. With this, okay, I can have yi transpose A, lambda psi also, A is not relying on index size, so lambda I and yi transpose here, okay, can be multiplied, okay, and C transpose, and when you apply lambda I equal 1 to m star, okay, so you know that when I equal 1 to m star here, okay, summation of lambda I from this equation is equal to 1. So the resulting of applying this operator over here, you get the same C transpose, okay, because summation lambda sub for all I is equal to 1. But for here, you end up having like summation lambda I transpose, okay, times A, okay, and minus C transpose has to be greater than or equal to 0. Or you can transpose on both sides. This become A transpose, okay, summation lambda yi transpose, okay. This one summation lambda I become yi because transpose, and you transpose it again, you become the original yi. Okay, and this is the constraint that you get, that A transpose y should be less than or equal to C. Okay, and that according to this is what, if you consider the dual form here, you can make A transpose y less than or equal to C. Okay, and when you consider this, it become A transpose summation lambda I transpose should be less than or equal to C transpose. The same as here, okay, A transpose y less than or equal to C. So we can conclude that the optimum y, okay, that can be written in this form by this substitution. Okay, this is objective function should be B transpose y, and then so therefore your y is summation I equal to m star lambda I transpose. Okay, and this one is also okay. Okay. A transpose summation lambda I transpose should be less than or equal to C transpose. Okay, so with this, by this observation, we can conclude that the optimum. Suppose that the primal solution reached the optimal solution, okay, for x, okay. Therefore, with the strong duality theorem now, C is equal to T, okay, here, and you can and equal to W here, okay. T and W should be equal here, so we can conclude that the optimum dual variable should be in this form. Okay, which means that I can use the dual variable by solving this Bender-Cut optimality cut model, okay, and obtain the dual variable according to each additional constraint of Bender-Cut, and you find just like a convex combination, because the lambda I should be less greater than or equal to 0 and summation is equal to 1. It's a convex combination for each y that you have found in each iteration, y star that you have found in each iteration. Okay, so this is the summarize that we can find the optimum dual variable by using this formula. Okay, and I have some illustration for you to show, okay, based upon this problem that we solved before in Excel, okay, this one, okay. As you might remember, this is a stochastic diet problem, and with this solve 17 iteration, okay. At first we solve at 10, and then we extend to 7, and a couple of clips ago I already showed you that the optimal solution is right here, okay, that 14511, okay. You can see that in each iteration, okay, you're gonna get the optimum y star here. And you solve it here. And every time that you solve, you're solving this model. Okay, this LP model. Okay. But this LP model has some additional constraint beyond the Bender-Cut constraint, which is the summation of the all decision variable has to be equal to 1, and all which I put it here, okay, the summation is, and all for each raw material here, okay, should be within the range here, okay. That's the range control for each decision variable. Okay, so what we're going to apply is that we are going to apply the concept here, okay, to find the optimum dual solution from this final problem here. But certainly if you solve this now, you cannot get the optimum solution, you know. Even though you can see that I already put, actually once you solve this, okay, as a linear programming, okay, in the model here, okay, we solve this, okay, and then you get what you call not only the optimum solution here, okay, I'll try to solve it again, okay, and show you, okay, we solve it, okay, certainly takes a while. And actually you can have what you call the sensitivity report here. And why we want this sensitivity report? We already have it here, okay. If I click that sensitivity, they will generate this report. Because this sensitivity report, you can find the value of the dual variable of, this is a dual optimum solution, okay? Dual optimum solution from solving this, okay, which is what we want. If you might remember that we discussed about finding dual, because you need the dual variable here according to the each optimality cut constraint, and find the convex combination of the corresponding y in that iteration, optimum y in that iteration, okay. So sorry, we go to the final. But the problem that we done in this problem is that for each cut that we already add, we didn't include any y star here. Okay? Not at all. We only have the y star of the final cut, which is this cut that we have the current one. So if you want to use this formula to do, you need to keep all the y value from the very first iteration to the latest iteration. Okay? And that's quite a work and quite require a lot of storage to install this y value, because this y value is sensitive. The size to store this data, if you go back and look at the original model, is rely on the number of rows in this model, which can be very large and very sensitive to the growing size of the number of scenarios based on all combination of the uncertainty. Okay, so this is what the problem that happened when you apply Bender decomposition. Because if you want to find the dual variable here, it takes a very large amount of memory to store all the y. And if the problem is that if m star keep getting larger value, okay, it will take you much more memory, okay, to keep this the vector of y, okay, for each iteration. Because at the end, okay, once the solution converges, you can use this the dual variable of lambda I, which in case of this in this problem, okay, you can look at the sensitivity report here, okay. You can see that the final value 1 here, okay, and this is the dual variable. You look at the shadow price down here. This one, this is a dual variable according to the constraint of summation of x is equal to 1, which is not our lambda here, okay, because you can see from the what we explained here, the lambda be dual variable according to the constraint, just the Bender cut, okay. So when you go back and look at the results down here, okay, so this is not the lambda I. The lambda I start from this one, the cut 1, cut 2, cut 3, okay. So this is actually, and you know that the first cut is down here and the latest cut, because we keep pushing it down, okay, to the cut number 1 here will be the latest one, and this is what we call the lambda value. Okay, and you can observe that the summation of this lambda value is quite pretty obvious here. Okay, if I can use the automatic sum here, I just sum up this 3 value. Okay, because the remaining, actually I can sum it all together, because this case is sum it all together, all possible cut that add. Okay, the corresponding shadow price, what is the result? You can expect that it has to be 1. Okay, you know why? Because we already showed that the summation of lambda I have to be equal to 1. It have to be all non-negative value here. Okay, so this one is a lambda. There's only 3 lambda here. Okay, and this one is not. Okay, so in order to find the dual variable here, okay, you need to solve until the final convergence of the lower bound and upper bound reach based on the Bender decomposition. And then every iteration you need to keep the optimum y that you solve. Okay, if you might remember from the Excel file here, is a value that you find in these 2 columns, YAL and Y star M. Because every time the new x apply, this one change. But now you have to keep it in every iteration. And then once you already detect from the sensitivity report here, you can use this as a weight. Okay, maybe convex combination as a weight average. Okay, for each y corresponding to each cut, and then that will be the resulting of the optimum dual variable according to the cut constraint, the cutting plane constraint. Okay, not the cutting plane, the optimality cut constraint of Bender decomposition. Okay, so I have done some extra work for this additional file we call copy of store diet raw 6 added. Okay, and this file you can find it in the lecture 1 Bender decomposition for 2-stage LP. You can download it from here. Okay, and the link of this drive data, okay, you can find it in the very first clip of introduction. Okay, I have added a message in that clip. Okay, and put the link down there so you can come in, and it's free and it's open for everybody to enter this first. Okay, to enter my online learning, and then you can click the lecture 1 here. You can access to all the information here. Okay, so the last file I'm going to show you is this file, the copy of store diet raw 6 added. Okay, and tell you what I have done with this file. Okay, you can see that we have an additional raw material we call raw material number 6 added here. Okay, this is a new problem that we say that suppose we have a new raw material added beyond the first 5 raw material from the previous problem, and this is the tolerance, the uncertainty of the amount of nutrient, okay, digested from each from raw material number 6, okay, according to the quality standard. Okay, and you can see that this is the one. Okay, this is the raw number 6, so I just add it here. Okay, so that you can transport it to MATLAB so easily, but there's no file of apply this in the MATLAB platform. Okay, I haven't done that, and I want to leave it to you to do it as a homework. Okay, so but in the network, in the Excel platform, okay, I already did this. Okay, by adding this. Okay, and this is still the old solution here based on the previous file of the final store here. Okay, this is the previous optimum solution here. Okay, 1 4 4 5, only in case of only 5 raw material. Okay, but in this one, okay, we add a new raw material here we call raw material number 6. But you might wonder that why I didn't add it after law number 5. I just insert between 4 and 5 here, because it's better than when you insert and then between the range of the old cells, okay? Because you don't need to change any coverage of the or the sum product formula to evaluate the left hand side, and including the calculation of the total cost here, because it will automatically cover this cell. That's the reason why I added here, okay? So this one you have a new raw material. At this moment there's no, because this is still the current solution uh, from the previous optimum solution here, okay? This is the optimum solution already. And this is what I did here, okay, when we add it here. Okay, we add the new raw material 6, and this is still the old file of raw material 1 to raw material 5, okay. We still doesn't have raw material 6 yet, okay. But in this case, okay, uh, the difference between this file and the previous file is that we keep the old y value here, okay. I compute the dual variable here for you, because for each iteration, okay, I'm gonna keep for each cut that had been added, you have y star al and y star am down here, corresponding for each cut. And then with this solution, you generate already how many? 24 cut, the same as the previous file that we did the final solution. But this one we didn't keep the old value for each for the y star for each corresponding cut. But in this one, okay, in the copy file here, okay, we add it all here together, okay. So when you have this y here, and with the sensitivity report, okay, you know that this, I show you from the previous clip, you know that this 3 value is lambda 1, lambda 2, lambda 3, okay. Okay, according to the latest one and previous one. And you might say, wonder that why do I keep, you need to keep all y, because when you look at this problem, you see that the old y, okay, normally you more effective for the new one. But you never know, okay. This one you cannot control. Just this example that the 3 reason one is an indication of the optimum solution. But it might go back. There's no theoretical point of view to guarantee you. That's why you need to keep all the y, okay. And this one, you can see that I already put this as a lambda 1, lambda 2, lambda 3, okay. But this one should be lambda 24, lambda 23, and lambda 22, okay, because as you know that when we add the cut, we put the previous cut, okay, to the to the higher index, okay. Okay, but this one should be the 3 most recent cut, okay. This is according to the, and this value coming from the dual variable here, the first 3 here, okay. I just copy it and put it in here, okay, in this check file. So and once you keep all the y here, okay, I can I can use this as a lambda 1, and you can have apply this to y here at cut number 1 and y, and also ym, and this one also the same, okay. Okay, because these two effective for both y at least and y star at most, okay. So and after that I just uh, use the Excel to compute this formula, this one, lambda I yi star, okay. And this is what I did in this file, okay. So what we did here is that we found the optimum y here, okay, yial, this is the optimum dual variable here, okay. Okay, and the yi star a is just this the combine of these two, this one plus this one, okay, which is nothing to do with the original y. You need both of this, okay. So this last two columns of y star AL and y star AM under the title sum product is the optimum dual variable. Okay, this one is the optimum dual variable according to all bender cut that have been generated. Okay, so this is the optimum y. Okay, and uh, it's a substitution of this is the optimum dual variable according to just this type of constraint. Okay, the constraint that you add plus u minus v. Okay, which is mean that you are handling the uncertain combinatorial of uncertainty that generate all possible value in the matrix A and in matrix in vector B. Okay, and you can see that in here. Okay, this is the illustration of this solving this formula, finding the dual here under the spreadsheet platform. Okay, under the spreadsheet platform. So you know that you need to install all the y here corresponding to each cut. With this diet problem, you have two type of y based on you have y star L and y star M. So you need to keep y star L and y star M for each cut. Okay, so this is the corresponding optimum y star for each cut, and then you do convex combination and then look at the sensitivity report of all the dual here. Okay, actually just you need to make a copy of all of this. Okay, and put it in here. Okay, and transpose it to all corresponding, and now you need it twice because y you have two type of y star Al and y star M. So you make a copy of the two of these together, and then you just did the sum product. Okay, of between the row of this is a corresponding dual form. Okay, dual variable. Okay, with each row here. Okay, the content of each row. So that become the sum product down here. Okay, and that's the resulting of this two column here will be the optimum dual variable. Okay, so this one is demonstration for the Excel format. Okay, but based on what the file that contain in lecture one. Okay, we we haven't added anything to find the, even though for this the last one that we consider is a Bender-Stowe diet here. Okay, there's nothing to do with the dual variable, optimum dual variable. Okay, and also for the previous one of Bender two-stage LP here also. Okay, for Bender two-stage LP here. Okay, no dual variable, optimum dual variable found. Okay, and even for the very first example that we try. Okay, you remember the mixture of 6 raw material here. There's no Bender dual variable finding in this program. So that's why I want to leave you as an assignment that, okay, you already see in the spreadsheet platform. Okay, we show you that in the spreadsheet platform we can do it, but in the MATLAB platform, okay, with all the file or MATLAB file that I put it here, except the direct LP. Okay, you can report. Okay, take a look at read the manual. You can see that how you can retrieve the optimum dual variable out of after you use the linprop object to solve the general LP. But for all the Bender program, okay, no additional routine coding you need to make in order for them to be able to find the optimum dual solution. Okay, so I leave that as a main homework for this lecture. Okay, beyond the previous one that I be assigning in other clip previously. Okay, and the thing that you will see and then should be considered is that uh, it might if M star is getting larger and larger, computing this will become you need a larger storage. Okay, and if you're dealing with a multi-million scenario problem, the computation of this can be huge, okay, and require a huge amount of memory and computing time, okay. So it can be considered as a research question, okay, for you to investigate or try to come up with the. This is just we use what we call the direct substitution. But I already foresee the problem when you're dealing with a large scale, very large scale problem. And if the problem is not converged smoothly, just like what we did in the example, like in 24, if suppose it's the first example, as you might remember, you require 80 convergence, okay? When you keep getting more variable, you might, the convergence rate, okay, the number of cuts can be getting larger and larger, okay? And the computation of the optimum dual variable can be a problem if you want to solve. So this is what the thing that when you take a look at the original paper of Bender, he he didn't discuss about this problem. As we told you before, that he didn't even mention about the application of that idea to the paper of Danzig's the linear programming under uncertainties. But people who using it found out later that these two papers is applicable and very efficient for each other. But that's for only the primal problem. But for the dual problem, you can have when problem getting larger and keep growing, the amount of time and amount of memory required to compute this dual can be uh, getting more expensive. Okay, so if you want to take a look at some initial research problem is that if you can come up with something nice to save the memory and also to develop some kind of quick computation as compared to the direct substitution for the formula to improve the efficiency to compute the optimum dual variable once you're using the Bender decomposition for the two-stage or even in the future multi-stage LP resulting from the original Danzig's model of linear programming under uncertainties. Okay, so this one let me mention to you again for the file that we put in all the MATLAB file here. No, we didn't add this routine, but we have some illustration to compute the formula. Certainly it was on the PowerPoint file here, okay? Show the formula and also in the file of copy store diet raw 6 add here. And actually, let's go back to the Excel file again, okay, for this one. This one we find the optimum dual variable, okay, according to the original 5 raw material. But again, this problem, we add a new raw material we call raw material number 6. And so is how come this the additional raw material 6 with the generated for all possible just 1156 scenario according to the original problem that we used before. Is this gonna well worth it to apply or rearrange the optimum solution again by adding some value of raw 6 and reallocate the other raw material amount and that you can reduce the total cost here. Okay, so I have another file here, okay, that I did, okay, and actually it was done by student last year, okay. This is an assignment for student last year that they did find the optimum solution, okay, when you add this raw material number 6 and also with the total cost here, okay, certainly the total cost reduced it, okay, when you add raw material number 6 in. But this is what you need to do. You need to, okay, this is the convergence of the results based on the Bender cut, and it will require you 47. You see that now the number of decision variable increased from size to 6, That's what I told you before, that the convergence rate become more stubborn as the number of the first stage decision variable grow. Okay, so this one you require 47, and again this one have no optimum dual variable here. Okay, so again this file you can check it back and restart doing it again 47 times. Okay, and each time you can repeat what we did here in the check sheet here. Okay, to repeat what we did here. Okay, and come up with the optimum dual variable here of YAL and YAM. Okay, and actually this one is the additional one. I want to check whether the result is correct or not by checking that once you get this optimum dual, you get the objective function equal to the primal problem here that we solve here. So to guarantee that okay, this is the correct answer of Y. Okay. One other way that you can compare is that you can set the small scale problem and then you can run on the MATLAB directly using linprop or even using the open software and see the dual variable and compare to the result that you get from the Bender decomposition. Okay, and again this one is already lack of both Excel platform and the MATLAB platform. Okay, in Excel platform, okay, I encourage you to try to find the optimum dual variable here for this problem. Okay, this one should be the one that you consider here. Okay, find the optimum dual variable on this sheet of optimum raw 6 by by looking back at the check file, check sheet. Okay, the second sheet here. Okay, and repeat the process, but it will be more difficult to do under and took more time when you did on the uh, Excel format, unless you be able to write a VBA macro to help you. Okay, but if you keep doing manually, okay, this one you need to do it, go back and repeat doing it again 47 times, and for each time you need to uh, keep the value of y star a and y star am. Okay, and then you separate it and make a copy just like what we did in the case of 5 raw material. Okay, and then in the final solution that for this one. Okay, this one is the final solution. Okay, you need to have a lambda value, the go back and then have some sensitivity report, but remember that this is the optimum sensitivity report. Okay, not for this problem, not for this problem, but it's a sensitivity report for the old problem. Okay, when raw only when you have only 5 raw material. So in this one you need to compute it again, and then you you can replace it. I think I can show you a little bit when we solve it. Suppose I solve it. I didn't put the formula, so it's just a waste of time. But I think that you can do it by repeating using the formula from the check and apply here. Okay, and once you get the solution, you check the sensitivity result. Then we add another sheet called sensitivity report 2, since you already have one. Okay, and that time you can go back and check something similar to what we did in sensitivity report 1 by checking the result of lambda. Okay, okay, and then you can once you get the lambda from sensitivity report check, you can come back and then you can repeat what you did here and try to what we did. You haven't done anything what I did here in this sheet, and then you can get the optimum y here. Okay, so in the sheet of the optimum raw 6 I encourage you to repeat doing it, finding the optimum dual variable for this one. Okay, and certainly the main point is that the big homework is that when you add it to the original Bender store diet here. Okay, because the original Bender store diet from the previous clip
we just solve for the primal solution. But if you want to find the dual, what's going to happen? And if you keep increasing the size here, let's say if you apply the 1 million, you might facing some of the higher storage requirement to keep the all the possible y value in the optimum y, this one. Okay, I think you can check with this. I just gonna increase here. Okay, this one, the yix here. Okay, you just in this one for the new iteration you get the new y replacing the old one. But the from the procedure that I showed, that you need to find a way that for each iteration you're going to keep y for all y, and then at the end, toward the end, at the final stage of solving the lin prop, okay, in the second one you need to find a way to retrieve the dual variable from this one, and then once you get that, you use a convex combination of all the y that you collect with the dual variable when you leave the loop, of the do y here, okay, when the gap approaching zero, and you can apply and use the formula of here, okay, to find the optimum dual variable. Okay, that will be a more challenging assignment. Okay, okay, when you did it on try to modify this program, the Bender store diet. And also, once you know this, you can go back and modify with Bender two-stage LP and refer to the first example of Bender two-stage LP exam. Okay, and I think that this is the huge amount of work that so it's all up to you that how much you can do for this type of homework. As we told you before that we are going to evaluate you toward the end of the semester by based on the work that you're submitting, and the work that you're submitting are all based on for each lecture, okay, what you have studied, and can you add up doing something else beyond what we already do in the clip, what we already do or did in the clip previously. Okay, so that should wraps up, okay, for all detail for lecture one. Okay, for the next clip we will move on and start to give you the detail of the lecture two. We still working on the Bender decomposition, but it's going to be the problem with kind of multi-stage model. And I give you a hint a little bit that we're still not very far from the classic paper of Danzig, okay? Because the problem that we are going to study is based on the model that in the example 3 here, the 3-stage or multi-stage in general here. But the problem is pretty similar to this example 3 here, okay? And you will see that there's some difficulty based if you that cannot our existing procedure from lecture one cannot be allowed to solve this type of problem. So we need to develop a new way to come up with the to make it more efficient to solve the problem. Okay, I hope that you go back and review all the detail in lecture one first, and then next time we'll start in the next clip the detail of the lecture two. Okay, from okay at this moment, okay, I'm gonna end this section. Okay, and see you in the next clip, huh? Okay, and see you.